In the last section of Module 4, we are going to talk about bisectors, medians, and altitudes. First, there's a couple definitions we have to talk about first. First, we have concurrent lines, which is when 3 or more lines intersect at a common point. And then the point of concurrency, which is the point of intersection of these concurrent lines, which we will see these two definitions are going to come in handy when we talk about some definitions. So first, let's talk about a median, which is a segment whose endpoints are a vertex of a triangle and the midpoint of the opposite side of the vertex. Then we also have something called a centroid, which is the point of concurrency for the medians of a triangle. Basically, the centroid is where all of the medians of a triangle intersect. And there is a theorem that goes along with where these medians intersect. There is a relationship that exists, and it states that the centroid of a triangle is located 2/3 of the distance from a vertex to the midpoint of the side opposite the vertex on a median. So in our triangle ABC, I'm going to draw the 3 medians. And these aren't going to be exact, but they're going to be close. So BD, AE, and CF are going to be the medians in our triangle. And then our point G is the centroid. It's where all of them intersect. So for example, for our centroid theorem, we know that BG is 2/3 the length of our median BD. Also true for AG is 2/3 the length of the median AE, and then CG is 2/3 the length of its median CF. That's basically what the centroid theorem states. So in our first example, we have points S, T, and U are the midpoints of segments DE, EF, and DF. We want to find the length of X. So X falls along the median DT. So we know the centroid A means that the length DA is 2/3 the length of our entire segment. So we know DA equals 2/3 the length of our median DT. So we can use this to find the length of the median, since we know the length of DA, to help us solve for X. So we have 6 equals 2/3 of DT. Multiply both sides by 3, we get 18 equals 2 times DT. Divide by 2, and we get the length of the median being 9. Now that I know the length of the entire median, that will help me find X. So since DA is 6, that means AT has to be a length of 3, since it's the rest of the median, which means that 2x minus 5 is going to equal 3. So 2x minus 5 equals 3. I can now use this to solve for x, so we are going to add 5 to both sides. So we get 2x equals 8. Divide both sides by 2, and we get that x equals 4. So we used our centroid theorem to help us solve for the length of our median, which in turn helped us solve for x. Next, we're going to start talking about an altitude, which is a segment from a vertex to the line containing the opposite side and perpendicular to the line containing that side. And then the intersection point of the altitudes, it's called the orthocenter. So the intersection point of the altitudes. So in our triangle XYZ, if I go from vertex Y straight down to the opposite side at perpendicular, and I can do the same for vertex X to its opposite side, straight down, to get another perpendicular line. And we can do the same from vertex Z to its opposite side. They all intersect at a point being the orthocenter. And not all of my lines may be exactly perpendicular, but they are close to it. So in our second example, we want to find x and the length of RT if SU is a median of our triangle RST. And then we want to know if SU is also an altitude of our triangle. So let's first start with finding x. Since SU is a median, it means that TU and RU have the same length, which is I'm going to use to solve for x. So we know 2x plus 24 is going to equal 5x minus 30. So first thing I'm going to do is add 30 to both sides. We get 2x plus 54 equals 5x. Subtract 2x from both sides. We get that 54 equals 3x. Then we are going to divide both sides by 3. And we get that x equals 18. Now, since SU is a median, it means that I only have to plug in 18 for one of my lengths, and then I can just multiply it by 2 to get the length of the whole segment RT. I'm just going to plug it into the 2x plus 24. So RT is going to be twice that length, so 2 times the 2 times x, which is 18, plus 24. So 2 times 18 is going to give us 36. Plus 24. 36 plus 24 is going to give us 60. Times 2, so RT has a length of 120. So we found 2 things in our problem. Next, we want to know if SU is an altitude. So remember, an altitude happens when it meets the opposite side at a 90-degree angle. So I have that the angle SUT is 4x plus 18. So if I plug in x for that and I get 90 degrees, I know that SU is an altitude. So we plug in 18 for x. We get 4 times 18 plus 18. And 4 times 18 is 72. And then we do 72 plus 18, and we get 90 degrees. So SU is an altitude. And it would be because the measure of angle SUT equals 90 degrees. In our third example, we want to find x and the length of ij if hk is an altitude of our triangle hij. So we're going to use the altitude to help us solve for x. So we know that 3x plus 3, which is the measure of angle HKI, has to equal 90 degrees. So we know 3x plus 3 equals 90. Subtract 3 from both sides, we get 3x equals 87. And then we divide by 3, and then we get x equals 29. Now that we know x, we can plug it in for the length of segments ik and kj, since they are going to add to give us the length of give us the length of ij. So ij is equal to ik plus kj, which is x plus 8 plus x minus 9. And if we replace the x's with 29, we get 29 plus 8 plus 29 minus 9. 29 plus 8 is going to give us 37. 29 minus 9 is 20. So the length of ij is 57. Lastly, we want to talk about perpendicular bisectors. So first, let's review what perpendicular lines are and what it means for something to bisect. So remember, perpendicular lines are lines that are at right angles We have two lines that intersect to form 4 right angles. And then for something to be bisected, it means to divide into 2 equal parts. So for something to be a perpendicular bisector, it combines the two. So a line, segment, or ray that passes through the midpoint of a side of a triangle and is perpendicular to that side. So notice how the definition of this does not include going through a vertex. So perpendicular bisectors do not have to pass through the vertex of a triangle. Since it has to be at the midpoint at a 90-degree angle, that doesn't always happen as it passes through a vertex. So if I look at my triangle IBG, if I draw the midpoint along the side BG so that I create 2 congruent segments, and then I draw the line that meets it at a 90-degree angle, notice how it passes through the side IG. Sometimes the perpendicular bisector may pass through a vertex, but more often than not, it will pass through a side. And then the circumcenter is the point of concurrency of the perpendicular bisectors. Of a triangle. Also, the orthocenter and the centroid, which were the intersection of your altitudes and medians, they always were inside a triangle. And with circumcenters, since the perpendicular bisectors don't have to go through a vertex, it also means they could intersect outside of a triangle or inside of a triangle. So the circumcenter doesn't necessarily have to fall inside of a triangle either. So we have one last theorem to talk about, and that states that any point on the perpendicular bisector of a segment is equidistant from the endpoints of the segment. So for example, we have segment CD. If I construct my perpendicular bisector going through CD at, let's say, point E, means that CE and ED are now congruent. So we have that CE is congruent to DE. So as you're completing the assignment over the medians, altitudes, and perpendicular bisectors, please ask for help on any problems that you are having trouble with.